Now discuss an all-important theory in thermodynamics called the kinetic theory of gases. Now, in this context, you must also appreciate how scientific theories evolve, how scientific theories take shape, how they are tested, how they stand the test of time, how they get modified, how experimental results are often used to test the theories, and so on. Now, what does kinetic theory deal with? Kinetic theory of gases is an attempt to describe how gases behave. Now, is it possible for us to go among the gas molecules to see exactly how they behave? You see, direct observation is very difficult. In fact, one of the first studies done to find the behavior of molecules was actually Brownian motion, the motion of molecules of liquids. Because you cannot really see molecules, you have to make a lot of assumptions. So, kinetic theory of gases, we don't know how molecules look like, but based on our observations in the large scale, we're going to depend on some intelligent assumptions that we make. And we're going to build a theory based on those assumptions. And the theory will yield some results which can then be tested. And depending on the results of the test, we can then decide, is the theory a good theory or a bad theory? If it is not a good theory, we need to come back and change our assumptions. You see, this is how scientific theories work. And these kind of assumptions we very often called hypotheses. So in this case, what do? We base our theory on certain, intelligent assumptions. Kinetic theory of gases make the following assumptions. Now look at the assumptions kinetic theory make. A gas is made up of identical spherical molecules which are in a state of random motion. And Newton's laws of motion can be applied to explain their motion. In other words, these molecules behave like any other objects. In other words, when they are subjected to forces, Newton's law of motion will apply to them. Now, what is the second law of motion? Anybody recall? Well, the second law of motion deals with the change in momentum of an object when subjected to a force. It says the rate of change of momentum is proportional to the force acting on the object. In fact, we defined unit force in such a way that force is a direct measure of the rate of change of momentum. We are going to use that in this class. So, rate of change of momentum is a measure of the force acting on a molecule. We assume that Newton's law of motion can be applied to the motion of these molecules. Assumption 2, the volume occupied by the molecules is very small when compared to the volume of the container. If you take a container like this, and if you squeeze all the molecules in here into a small space, that space will be very small compared to the total volume of the container. The volume of one molecule is so small compared to the volume of the container. Third assumption, the molecules undergo elastic collisions. What are elastic collisions? You recall the definition of elastic and inelastic collisions. You see, all collisions conserve momentum, but only elastic collisions conserve kinetic energy. So when the molecules collide, momentum is conserved, also kinetic energy is concerned. Molecules undergo elastic collisions with one another and also with the walls of the container. And the pressure exerted by a gas is actually due to the changes in momentum they impart on the walls of the container. They are hitting continuously on the walls of the container. Pressure exerted by a gas is due to the hitting of these molecules on the walls of the container. You remember we said at absolute zero, at 0 Kelvin, a gas ceased to have any pressure. Why? Because these molecules cease moving, and when they are not moving, they are not hitting the container. They are not exerting pressure. So pressure exerted by a gas is actually due to the collision of these molecules with the walls of the container. We are going to use that to derive an expression for pressure. We will use this assumption to derive an equation for pressure exerted by a gas. You see that? And then we can test that law using the gas law that we have discussed and also many other concepts that we know are true. And then we can test the validity of these assumptions. Assumption number 4. The forces between molecules are negligible except during collisions. In a gas, the molecules are absolutely free from each other's influence. There is virtually no intermolecular forces. You see, in a solid, intermolecular forces are great. In a liquid, again, the intermolecular forces are quite considerable. In a gas, the intermolecular forces are non-existent. In other words, the potential energy is a maximum. Is that right? They exert no force on each other. And our theory is going to be built on these assumptions. Well, we had actually looked at how gases behave when I showed you how temperature depends on the kinetic energy. Now here I have an illustration of the assumptions that we made. That the gas molecules are spherical and they are in a state of random motion. They hit against each other. They hit against the walls of the container. The volume occupied by one molecule is so small compared with the total volume that the space occupied by a molecule is very, very small. All right, what else did we say? We said these molecules interact in such a way that they hit against each other, but except at that time, they exert no force on each other. The intermolecular forces are virtually non-existent. And also I told you the pressure exerted by a gas is due to the hitting of these molecules. You can see they actually hit against the walls of the container. All right? Now, these are the assumptions on which we are going to base our theory. These assumptions we made, we will now use to obtain an expression for the pressure exerted by a gas. All right? Now, the figure shows a box containing a gas. Now here, this is the kind of box that we have, and this is the area A, and it contains a large number of molecules. And you must understand that the speed of these molecules, they are all moving at random. So there is no way you can look at a molecule and say, all right, this is going in the X direction. No, the speeds are distributed randomly. All right? Now, let there be n molecules. Let the total number of molecules in this box be n. And let the mass of each molecule be small m. So watch all these assumptions that we make. Now, we assume that the average velocity of a molecule is v bar. Now why do we have to say average velocity? Because not all molecules have the same velocity. They all have different velocities. The distribution of velocities will keep changing. So we will take for our purpose that there are a total of n molecules in the container. Each molecule has a mass m and has an average velocity v bar. Okay. Since the velocity is in any random direction, we assume that v sub x is the average x component of this velocity. You take a molecule, the velocity of a molecule can be at any random directions, but it has an x component, a y component, and a z component. So we are going to concentrate on the motion of this molecule in the x direction, and then we can take the y and z components later on, right? So let v sub x be the x component of this average velocity. Alright, so you got a molecule there, its velocity is v sub x. If uppercase V is the volume of the box, the number of molecules per unit volume, what would that be? If the volume of this box is V, and how many molecules are contained in that volume? There are n molecules in that volume. Therefore, what is the number of molecules per unit volume? Will be n over V. N over V now represents the number of molecules per unit volume. Let A be the area of the side of the box on the right. This area, let this area be A. Just like the box I showed you, this area is A. That means we are now, since we are talking about the average x motion of the molecule, we are now going to say these molecules are moving towards that wall with that average x velocity. When the molecules have an elastic collision with this wall, they just reverse their velocities. We said the collisions are elastic. That means when they collide, they don't lose energy. So if a molecule comes towards the wall like this, they collide and move away with the same speed. They don't lose speed when they collide. Is that right? Now, like this. Okay. The momentum of a molecule in the x direction, if you have a molecule that has the velocity, look at this. This molecule has the velocity v sub x. Its momentum in the x direction is m times vx. Now, the momentum of the molecule after collision, as the molecule approaches the wall, its momentum is mvx. And after collision is going to move away. That means its momentum is now reversed. Its momentum after collision is negative mvx. Therefore, what is the change in momentum of the molecule? This is the initial momentum mvx. The final momentum is negative mvx. The change in momentum is mvx minus negative mvx. So we have delta px. What does delta px stand for? The change in the momentum, equal to 2 mvx. So every molecule that hits the wall of area A will experience this change in momentum, that is 2 mvx. There you are.